everyone, this is Talk-Panpan Cai from the National University of Singapore. I'm studying the problem of interacting with a crowd of human participants. In such scenarios, drivers can be fairly aggressive. They behave differently from each other, and when they form a crowd, the motion becomes highly uncertain. Crowd driving is not only important in itself, but also uncovers a broader research question. How do we perform large-scale decision-making in highly dynamic and interactive environments? I'm going to discuss this question from the perspective of modeling, planning, and learning. We identified 3 factors that govern crowd behaviors, including kinematics, collision avoidance, and the road context. We modeled these factors in a unified velocity obstacle framework to produce an efficient motion model. We have embedded this model in our open source simulator, Submit, that can simulate traffic crowds in urban maps from any location in the world. If we further condition our motion model on hidden factors, such as human intentions, we can also infer a joint belief over those critical hidden information. To plan using this belief representation, a principal solution is POMDP planning. However, the complexity of POMDPs grow exponentially with the problem size. For large-scale problems, the complexity can easily become intractable. To scale up, we can leverage both CPU and GPU parallelization. Our planner HyP-DESPOT performs parallel tree search in the CPU and parallel Monte Carlo simulations in the GPU. By doing so, we have achieved hundreds of times of speedup in large-scale POMDP problems. And we have successfully applied it to driving among pedestrians, urban crowds, and also a real robot platform. Now, let's see how learning can come into play. The key observation here is that the search steps bring main problems in large-scale planning, including computational complexity, the coverage of samples, and the compounding model error. Therefore, we need to think locally and learn globally. This means to constrain search to short-term futures and use learning to account for long-term futures. For example, in Let's Drive, we learn global priors in the offline stage and apply these learned priors to synthesize new policies in the online stage. The key here is to guide the online belief tree search using the learned priors. Here, we use policy network to guide action selections and use the value network to replace rollouts. This integration enables Let's Drive to significantly outperform either planning or learning alone. To wrap up, in order to model large-scale things, we need to first identify the key uncertainties. We can leverage massive parallelization to scale up to large-scale planning. Finally, we can integrate learning by thinking locally and learning globally.